Hello, my name is Jasmine Deakin and this is my presentation on the electromagnetic spectrum. In this presentation, I will be covering electromagnetic waves and their properties and principles, infrared radiation, microwaves, the use of X-rays in medical applications and their hazards, visible light, ultraviolet, and the biohazards of ultraviolet and infrared. Electromagnetic waves. An electromagnetic wave is an electric field and a magnetic field travelling together through a vacuum velocity of 300 million meters per second. They have a variety of wavelengths and frequencies at multiple amplitudes. And our human eye has developed to detect a small band of these wavelengths in the centre of the spectrum, as we can see just here. We detect different wavelengths as different colours. A magnetic electric charge generates a field, whereas a magnetic field induces electric movement, producing electric current. An electricity cannot exist without magnetism, and magnetism cannot exist without electricity. In an electromagnetic wave, as we can see here, the electric field and the magnetic field run perpendicular to one another. And this is the direction that it's travelling in. Infrared and ultraviolet are the first wavelengths of the electromagnetic radiation that we cannot see. As you can see here, either side of the visible light, and then it extends up. Although we can't see these forms of radiation, we can sense some of them. For example, heat from the sun. Now, common things that use electromagnetic radiation are radio, microwaves, heaters, mobile phones, and sight from the eye. We need to understand the shapes and measurements of electromagnetic waves, and there are four properties of waves. These are wavelength, frequency, velocity, and amplitude. Wavelength is the distance between the two peaks, as we can see here, and this is measured in meters. Frequency is the amount of peaks per second as the wave is moving. This is measured in cycles per second. So one cycle is when the wave moves from the baseline here up to the crest, down to the trough, and back to the baseline where it started. That counts as one cycle. This is measured in hertz. So 1 hertz is 1 cycle per second. And wavelength and frequency are symmetrically opposite. So when one of the value increases, the other decreases. So for example, when these two waves are traveling together, these two waves are traveling at the same speed, they are inversely related. The wave with the shorter wavelengths, which is this one, has the higher frequency, whereas the longer wavelength has the lower frequencies. And the third property is velocity. So this refers to the speed of the wave. The wave equation is velocity equals frequency times wavelength. And the best way to work this out is to make a triangle. If you want to find out the speed, you just simply cover that one up and times the bottom two together. Whereas if you wanted to find out the frequency, you would cover that one up and divide the other two. Amplitude is the fourth property, and this measures the power within the wave, and it's the distance from the baseline to the peak. So for example, a guitar amplifier strengthens the weak electrical signal from the guitar to produce more sound, so the amplitude of the wave increases. Okay. Infrared radiation. Infrared radiation is a type of radiant energy that is invisible to the human eye, but we can feel it as heat. Infrared radiation is in the region of the spectrum where the wavelengths range from about 700 nanometers to 1 millimeters. And we can see here it's just outside of visible light on the spectrum. The distance an infrared signal can travel is based on the strength of the transmitter. There must be a direct line of sight between the transmitter and the receiver. So for example, a TV remote here is using infrared, and the receiver over here cannot travel through a human. Aluminium foil is a strong reflector of infrared radiation, and this is why individuals place it behind their heaters on exterior walls to reduce heat loss. So if you can look in this diagram here, this is double-sided reflective foil, and you can see that the heat is reflecting 95% of the radiant heat, and it's only emitting 5% of the heat out. Certain substances absorb infrared radiation, like water vapour, carbon dioxide and methane. The Earth's atmosphere absorbs the longer wavelengths, which we know as the greenhouse effect, where infrared radiation is emitted from the Earth, allowing it to heat up, as you can see in this diagram over here. Some of that is reflected in the atmosphere. Applications of infrared. So household items such as TV remotes and electric heaters. Medical applications for observing change in blood flow in the skin. Military use infrared radiation for searching targets, surveillance and night vision. And environmental applications like monitoring the Earth's temperature and weather forecasting. Microwave radiation. Microwaves are positioned on the electromagnetic spectrum between infrared and radio waves, with wavelengths ranging from 30 centimeters to 1 millimeter. Applications of microwave technology include satellite transmissions, mobile phone networks, Bluetooth. Most familiar in the context of microwave ovens, conventional heating transfers energy from the outside inwards, whereas microwaves penetrate the food, and the vibrating electromagnetic field causes molecules such as water to vibrate as they align themselves with the moving field. So you can see in this diagram here, the microwave is transferred the electric energy and the friction of heat to heat or cook the food. So you can see the electromagnetic waves are vibrating this with the molecules inside, and that will heat or cook the food. Terrestrial microwave transmission range will travel a distance of around 30 miles. However, a transmission by satellite links will extend this to hundreds of miles. Bluetooth is a close-range microwave application working on line of sight. So similar to infrared, microwaves do also work on a line of sight, but unlike infrared, microwaves can transmit through walls and other objects. Another difference between them is that microwaves can usually communicate with each other regardless of the manufacturer, whereas infrared devices usually only work with their own manufacturer equipment, as you might have found with TV remotes. Use of X-rays in medical applications. X-rays are a type of electromagnetic radiation that carry a high frequency of waves, more energy, and penetrate further than ultraviolet radiation. And this is they reside in here in between UV radiation and gamma rays, as you can see there. Applications of X-rays include examining broken bones and joints, progression of teeth, and CT scans. These are 3D scans of the body requiring an X-ray source and detectors on the other side of the body. It is then computerized to reassemble images to create the 3D scan. Hazards of X-rays in medical applications. There are a number of hazards that come with X-rays. For radiographers X-raying patients on a daily basis, the dangers need to be assessed. They need to be wearing the correct protection and ensure that in the correct areas whilst the X-rays are taking place. They will usually wear a dosimeter badge to monitor their exposure to dangerous radiation throughout the day. X-rays can kill cells or trigger cancer cells at some point in the future, and the energy of X-rays can knock electrons out of their atomic orbit and cause change in the molecules. In a dental X-ray, the patient is obliged to wear a protective lead-lined apron or bib to shield their vital organs from unnecessary exposure to the X-ray. Although all these hazards are considered by medical professionals, we are surrounded by radiation from the sun, rocks, and different substances on Earth, which make their way into the food chain. It is worth noting that routine X-rays give the same exposure as 3 days exposure to natural radiation from the environment. Visible light. Visible light is only a section of the electromagnetic spectrum that we can see, usually defined in the range of 400 to 700 nanometers. White light, as we know it, consists of various wavelengths of electromagnetic radiation, which we recognise as colour, as we can see here. If visible light penetrates a glass prism down here, it is refracted and separated into an array of visible colours. The shorter the wavelength of light with the higher frequency, the more it is refracted, and as a result, red light is refracted the least, whereas violet light is refracted the most. And this is what we know, we recognise as a rainbow, of course, as you can see. Applications of visible light. Eyesight, allowing humans and animals to see our surroundings, although too much light can cause damage to the retina in our eyes. Vehicle-to-vehicle communications, indicators and warnings to avoid accidents. Television, computer and phone screens, and lasers to use in such things as surgery and CD players. Visible light also plays a crucial part in crime scene investigations. White light was the main source of search up until a few decades ago, and it is still used today. Lasers and high-intensity lamps are used in forensic alongside new technology. Ultraviolet. Ultraviolet light is between visible light and X-rays, as we can see here. on the electromagnetic spectrum with a wavelength between 400 nanometers and 10 nanometers. Unlike visible light, we are unable to see this with the naked eye. And UV light has shorter wavelengths than visible light with higher frequency, creating a higher energy. And some animals are actually able to see UV light, such as certain birds, fish, bats, and butterflies. Some applications of ultraviolet. To treat vitamin D deficiency, which is of course very important for strong bones. The use in sunbeds to recreate sun waves, but too much time in the sun or a sunbed can cause damage to our skin, causing it to redden and blister, and this is caused by the UV light. To kill microbes, hospitals use UV lamps to sterilize their equipment, as well as food and drug companies to sterilize their products before sending them out. In forensic investigations, UV light is used for multiple purposes, such as analysing questioned documents and paintings, eliminating fingerprints at crime scenes, and tracing evidence on clothing. Body fluid and perspiration give off fluorescent lights illuminated by a source of UV light. Biohazards of ultraviolet. Ultraviolet radiation can be extremely damaging due to having shorter wavelengths and higher frequencies. Carrying more energy means they are more penetrating. So UV radiation is known as the cause of skin cancer, skin aging, and eye damage. As we can see here, this level of radiation can penetrate into the tissue and disrupt the DNA of cells, making them unable to perform vital functions, which makes them unable to reproduce, resulting in them dying out. Too much exposure to UV lights, for example, someone that works outside all day, can cause these chemical changes in the DNA, resulting in mutations and cancerous development. Biohazards of infrared. Infrared radiation is emitted from hot objects and can heat up anything it touches. Infrared radiation can therefore cause skin blisters and burns to the skin. For example, if you were to touch a hot kettle. Intense infrared radiation can also cause damage to parts of the eye, such as the cornea and the retina. Protective goggles are given to patients receiving infrared radiation therapy, which is over 1,000 times more powerful than a TV remote. Prolonged exposure to infrared radiation causes a gradual yet irreversible damage of the lens. That is my presentation. I hope you've enjoyed it, and thank you for listening.